Okay, let's start. Today we're going to talk about the matrix operation. Until this week, we have learned what is the linear equation and how to solve in the systematic way. But from this week, we will talk about the matrix operation that solve the linear system in a matrix domain. Okay, so before starting, we have two notifications. The first one is the homework. The homework one is already announced in the Blackboard in last week. Then the due date of this homework is the April 19 until midnight. So please start the homework as much as possible. And there will be no midterm exam in this semester, as I mentioned to you in the last week. So please keep in mind. Okay, let's start. So first of all, let's think about the matrix A with the size m by n. So in this case, this matrix consists of the m rows and n columns. What does it mean? So the matrix A looks like this, right? So there have m rows with n columns. Okay. Then the scalar entry. The scalar entry in the ith row and jth column denoted by a subscript ij, and it is called the I comma j entry of the A. Okay, let's see the example. Let's say here is a matrix A, something like this. As we discussed, the size of the matrix is m by n, right? And in this case, this color value is represented by A11. And what about the row y? Okay, let's say the row y and column j. So in this case, something like this. So in this case, it can represent aij, right? So what about this? This is the first row, right? First row with the jth column, so it should be a1j, right? What about this? In this case, ith row with the first column, right? So it should be like this. Then finally, in the last row and last column should be amn, something like that. So some arbitrary matrix can be represented something like this. Yeah, something like n, right? So it's very intuitive, right? So, and then each column of A, what is column of this matrix? Here, 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 right? So the matrix A consists of the what? N columns, right? Something like this, right? So each column of the A is the list of the m real numbers, which identifies a vector in Rm space. So what does it mean? So this one vector is in Rm space. Okay, so it means that each column vector consisting of the A11, A21 through the AM1. So is in Rm space. Okay, so this is the definition of the matrix operation, right? So as we discussed, this arbitrary matrix A consisting of the n column vector, right? Something like this, right? And the number Aij is the ith entry of the jth column vector Aj. Okay, like here, like this, right? So we already discussed this in the last lecture, right? Then what is the diagonal entry? What is the diagonal entry in the n by n matrix A? Let's say there is the m by n matrix. Okay, so in this case, diagonal matrix. Yeah, diagonal matrix. Here, something like A11, A22, A33, something like that. So this is called the diagonal entry. Then they form the main diagonal of the matrix A. Okay, something like this is the diagonal entry in the arbitrary matrix. What about the diagonal matrix in the n by n square matrix? Let's say we have another matrix B with the n by n, the n by n square matrix. In this case, what is the diagonal entry in this matrix? Here, right? So let's say this is a P11, P22, Pn, right? So in this case, and then there is whole zero here. Then in this case, this matrix called the diagonal matrix. Diagonal matrix, something like this. This is also easy, right? And an example of the n by n diagonal matrix is the n by n identity matrix. Okay, what was the identity matrix? Something like this, right? With the size of n by n. So in this case, there is only non-zero entry on the diagonal. So this is the special case of the diagonal matrix, right? And then there's another matrix here, n by n matrix, whose entries are whole zero, is called the zero matrix. So what about the zero matrix? So zero matrix, something like the matrix that consisting of the whole zero with the size n by n. By n, okay? So this is an example of the zero matrix, right? Then, okay. So we can say that the two arbitrary matrices are equal. Okay, let's say there is a matrix A and matrix B are equal if they have a same size. Okay, then their corresponding columns are equal. Let's say matrix A, something like T, matrix B, something like this, right? So first of all, the size of each matrix should be equal. Then their corresponding columns here should be equal. Then finally, corresponding entry should be equal, right? Here. So in other words, the two matrices are equal when each entry is the same. Here and here, here and here. here and here, like this, right? This is very intuitive, right? Then if two matrices A and B are n by n matrix, then the sum of A plus B, matrix A plus matrix B, is the n by n matrix whose columns are sum of the corresponding columns in AB. What does it mean? Okay, let's say we have a matrix A11, A12 through the A n by n, something like this, okay? And we have another matrix B, P11, P12 through the PMN, something like this. What about the A plus B? First of all, to find the sum of the A plus B, the size of the matrix A and matrix B should be same, and the sum of each entry will be the another entry in the A plus B matrix. So it should be A plus B11. What about this one? MMN plus PMN. Okay, like this. So this two term makes this one. Okay. So the output of the summation of the two matrices should also have the same size. In this case, okay, let's say that this is n by n, this is n by n. The A plus B should be also n by n. Okay, so this is the summation, right? Okay, for example, okay, let's say there is a two matrix A is something like this, matrix B is something like this, matrix C is something like this. Okay, first question is find the A plus B. Okay, what is A plus B? The summation of each entry. So in this case, plus 1, 0 plus 1, 5 plus 1, negative 1 plus 3, 3 plus 5, 2 plus 7. So in this case, 5, 1, 6, 2, 8, 9, right? So this is A plus B. What is the A plus C? What is A plus C? Okay, let's add each entry 4 plus 2, 0 plus 0 minus 3, minus 1 plus 0, 3 plus 1, and 5 plus what? There's no entry in here, right? Right. So in this case, it's 0? No, because there's no entry in here, so it's not possible. So in this case, it's not possible. So it means that because the size of the matrix A and matrix C are different, so the A plus B is possible, but A plus C is not possible. Okay. Okay, let's move on. There's one more operation, the scalar multiplication. Okay, let's say the R is a scalar value and A is a matrix. Then the scalar multiple R times matrix A is the matrix whose columns are R times corresponding columns in A. What does it mean? Okay, let's say there is a matrix A 1 1 1 2 2 1 blah 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 m by n mn, and there is a column scalar value R here. Then in this case R A means R times each entry. In this case, something like this, something like this. Okay, something like that. Okay, so I move quickly this chapter because I think that this is very intuitive. So if you have any question, please send me an email about this one. Okay. Okay, so there are some property. related to the summation and scalar multiplication in the matrix space. Okay, so let's say there are matrix A, matrix B, matrix C, and with the same size, and there is a R, S scalar values are here. Then each property, something like this, should be satisfied. First of all, A plus B is equal to B plus A. Okay, and this is very intuitive, right? So there's a proof. No. So let's prove the first one. How can we prove? Okay, let's say matrix A matrix B then A plus B means then there is the there is some rule that something like P11 plus A1 in the real value property, something like this. So finally we will get the P plus A. So this is the proof of the A plus B equals the P plus A. This one, right? Then what is the second property? A plus B bracket A plus B plus C is equal to A plus bracket B plus C, right? Then what about this one? A plus 0. 0 means the 0 vector, right? So the size of this 0 vector should be the same as the size of the matrix A, right? So in this case, the output of this equation is the matrix A itself. Okay. What about this one? R times A plus B is equal to RA plus RB, right? Then what about this? Bracket R plus S times matrix A is equal to RA plus R here, yeah, SA. Okay, like that, and R times SA is equal to RSA. Okay, so as you can see here, like this one, Horo property can be verified by showing the matrix on the left hand side here has the same size as the matrix on the right hand side here. Then corresponding columns are equal, something like this. So I guess you can easily prove this property. So please try to prove this one by yourself. Okay. And by the way, this I usually give you some homework in the during the class, but it's not mandatory. So you don't need to submit this homework. But I strongly suggest you to do this yourself, because I can't I can't do horrible things during the class because we have the limited time. So I strongly suggest you to do it yourself. Okay, let's move on to the matrix multiplication. Okay, let's say we have a matrix let's say we have a matrix P multiply vector X. It transform vector X into the vector Bx. Okay, what does it mean? Let's draw some figure here. Okay, here is some space, and there is a input vector X here, and matrix multiplication on this one. multiplication by B can make the what? B times matrix X. So this is another vector, right? Then if this vector is then multiplied by the another matrix A, let's say there is another space here, and this point multiplied by the multiplied by A, then this point will be the A times B X point, right? So the resulting vector will be the A bracket B times X, something like that. Okay, so this is the definition of the matrix multiplication. So it means that by using the matrix multiplication, we can transfer or convert the input vector X into the another space, something like this, okay? So this is the concept of the matrix multiplication. We will discuss how can we compute this matrix multiplication element with each element. So let's see. Then this ABX is produced from the X space input X here to here, right? So this is the composition of the mapping. This is a linear transformation. What does it mean? So from here to here, there were two lines, right? Two transformation, right? This one and this one. So vector x to the a p vector x. This is the composition of the mapping. So it means that there is another mapping function, something like this, from the multiplication by AB. Okay, like this. So in other words, this value a times p x is equal to ab x. Okay, so this is the composition of the linear transformation or the linear matrix multiplication. So in this there is the so there is the equation something like this. So our goal is to represent this composition composite mapping as a multiplication by the single matrix a times b. Okay, so this is a concept of the matrix multiplication. Okay, so let's see the detail. Okay, let's say there is a matrix A with the size of the n by n and matrix B with the size of n by p, and then there is one more vector x in the RP space. Okay, denote the columns of the matrix B as something like this, and entries in the vector x as this. Okay, so what does it mean? So let's say we have a matrix A, something like let's say n by n, right? Then matrix B, P11, P12, P21, P22 with P and P, right? This is just n by n, right? So and then vector x should be x1 through the xp, right? Then the columns of the matrix B is something like vector 1 through the vector P, right? Something like that. Then what is the vector matrix B times vector X? We already know the matrix times vector can be represented as a linear combination of the column vectors in matrix B with the weight in the each entry in vector X. So in this case, this term is the vector 1 times x1, and this one is the vector pp times xp. So this is the linear combination, right? So from the linearity of the multiplication by a, we can compute the a times px as a times this one, right? From this notation, right? Then we can represent each term something like this, right? Because of the rule here, right? So please try to derive this whole property by yourself. So you have to use this property easily to follow this one. Okay. Anyway, so this a times px can be represented something like that. And what does it mean? The a times bx is the linear combination. So linear combination of the vector this one with the weight this one. Okay, so this is the linear combination of the matrix A times each column vector B. Okay, so it means that from here A times bx is going to be AB1 ABP times vector x. Okay, so finally, what does it mean? The multiplication by this one transform this vector x into the a times p times x, like that. So this is the way to compute the matrix multiplication. Okay, so from this concept, this notation, there is a definition. Okay, so let's say we have a matrix A with the size of n by n, and matrix B with n by p with the columns b1 through the pp. Then vector product, A times B is the n by p matrix whose columns are a times b1, a times bp, right? Why? Because it was the a times b times vector x, right? So in this case, this one should be same by this one, right? So we can represent the matrix A times B as a matrix A times the column vectors of the matrix B in the matrix B, and it will be AB1 through the ABP, right? So this is the definition of the vector multiplication. There's one more very important concept here. Okay, so because we already know the matrix size of the matrix A is the n by n, and size of the matrix B is the n by p, right? Then what is the size of the output of the A times B? First of all, the number of rows in the output should be M, right? Because the this is the same to the matrix A. Then what about the number of columns here? Should be P. Okay. Okay. So there are very important concept. So first of all, to compute the matrix multiplication, these two value should be same. Okay. We will discuss this concept in the later, but before that, we have to know these two terms should be same. Then these two terms will determine the size of the output as n by p. Oh, let's say this is p. Okay, n by p. Okay. So this is the rule of the matrix multiplication. Okay, so multiplication of the matrix correspond to the composition of the linear transformation. So in this case, okay, let's say there is a matrix C is equal to A times B. Then if we have the vector X, then what is the vector C times X? Let's say there is the output of the C times the X. Then we can say that there is the two transformation B times X and A times B times X, something like this. So these 2 points should be same. So it means that the multiplication of the matrix corresponding to the composition of the linear transformation. This one, okay? This is the concept of the matrix multiplication. Okay, so let's see the example. The question is to compute the A times B when A is equal to 2 by 2 matrix, something like that, and B is equal to this one. Okay. First of all, let's use this property. So we have to represent each column, this one, as a vector B1, vector B2, vector B3, something like that, right? Then we have to compute this one, so what is the A times vector B1? What is the A times vector B1? There is the matrix A with a vector B1, right? Because suppose 1, right? Then how can I compute this one? This value is this column times this column, right? So in this case, 2 times 4 plus 3 times 1. So in this case, the 8 and 3, so it should be 11, right? What about this one? This vector times this vector, so it will be the -1. So similar way, we can find the A times vector B2 here, A times vector B3 here. So finally, A times B is going to be AB1, AB2, AB3. So finally, this value, this vector will be here, this vector will be here, this vector will be here, right? So we can say that the output of the matrix A times B is going to be something like this. Okay. Okay. So if we go back to the size of the matrix, what is the size of the matrix A? What is the size of matrix A? 2 by 2, right? What is the size of the matrix P? 2 by 3. Then the output of the matrix A times B should be something like this one. So it will be the 2 times 3, right? So the number of rows will be the 2, the number of columns will be the 3, right? In the A times B. Okay, so this is the examples of the matrix multiplication. Okay, Okay, so there is a very important rule called the low column rule for computing the A times B. This is very important, but this is very intuitive. So if you understand what it is, you can easily use this rule to compute the matrix multiplication, something like this. Okay, here's a rule. If the product A times B define the entry in the row I and column J of the AB is the sum of product of the corresponding entries from the row I of A and column J of B. What does it mean? Let's see the example. Okay, there is a matrix A and matrix B and matrix A, B. Then we want to know the this value, the ij entry in the matrix A times B here, this one. Then how can we get this value? The row I of the A, row I of the A. This is a vector, right? And then the column J of the B, column J of the B. This is the another vector, right? Then this term will be the product of the corresponding entry. This one, this one, this one, this one, through the this one times this one, and the summation of the whole product will be the this one. In other words, this value will be the A I comma I1 times P1j plus A I2 times P2j through the A IN times P and J, something like that. So to compute this value, we have to find the product between this value, this value, this value, this value, this value, this value, and then summation of the whole output. So this is the rule of the A times B. So from here, we can know why these two values should be same, because okay, let's say this is the n by n matrix, and then this is the n by p matrix. The output is the n by p, right? But to compute this value, this vector and this vector should have the same size, right? So in this case, n as n, right? So this is the rule of the A times B, matrix A times B, okay? So this is very intuitive, okay? Okay, let's see the example. Find the entries in the second row of the A times B, where A is something like this, B is something like that. Okay, let's say the A times B. Okay, first of all, what is the size of the A times B? Because the size of the A was the 4 times 4. No, 4 times 3, right? Right? What about the B? 3 times 2, right? So first of all, these two values are same, right? So the size of the AB will be the 4 times 2, right? So the shape of the output, something like this. Is it correct? Right? Yeah. So let's see the first. What is the value one by one? From this rule, we can compute this value by this one and this one, right? So in this case, this will be the 2 times 4 plus negative 5 times 7 plus 0 times 3, right? What about this one? 2 times 1. You'll be second row times the first column here, right? So in this case, negative 1 times 4 plus 3 times 7 plus negative 4 times 3, something like this, right? What about AB 2? What about A times AB 2? This should be this row times this one, right? So what is that? What is that? Negative 1 times negative 6 plus 3 times 1 plus negative 4 times 2. So it should be 6, 3, negative 8. So it is just 1. Okay. So then what is that? Negative 4, 21. So 5. Okay. So this one will be the 5, and 2 comma 2 value is the 1. Okay, so you can find the the entry in the second row of the A times B, something like that. Okay, you can find the every point yourself using the similar way. Okay, so we have been talked about the matrix multiplication. Then let's find the property of the matrix multiplication. First of all, let's say there is a matrix A as with the m by n matrix, and matrix B C has the same size as a m by n. Then there is the rule. There is the indicate sum and product property, something like this. First of all, there is the associative rule. It means that A times BC is equal to the AB times B. This is the associative rule. Okay. The second rule is the left distributive rule. What does it mean? So A times B plus C is equal to A times B plus A times C, something like this. Okay, so this is also very intuitive, right? Then there is one more rule called the right distributive rule. It means that B plus C times A is equal to B times A plus C times A, something like this, right? And then with the scalar value r times AB is equal to the RA times A is also equal to the A times RB. Okay, so there is a rule, something like that, and there is one more rule. Because the size of the matrix A is the m by n, we can multiply the identity matrix of the size m by n on the left side on the matrix A and right side of the matrix A, like this, right? Because the size of the matrix A is m by n. Then we already know this is identity matrix, so the output of this two term will be the exactly same as the matrix A. Okay, So this is the property of the matrix multiplication.